sample, and time. Okay, you're never going to get an immediate fix to the problem. So where at all possible, prevent the problem. Tillage, again, is going to be kind of your backup when there is already compaction, or in cases where there's just no other option. That limited tillage is going to help you at least break up the compaction to start the remediation process. Remember that too much tillage, though, just gives you those loose particles that are going to pack together again immediately, and can kind of contribute to continued compaction or recompaction. So be careful not to overdo it with that tillage. Organic matter is always a good addition to soil to help prevent the packing of those particles so tightly together, and just overall contributes to the porosity of the soil. And with that organic matter, you're also promoting biological activity, and I've kind of shared with you that biological activity is a lot of what creates soil structure. Those granules formed by biological activity, the channeling that occurs in the soil that creates those macropores, a lot of that's from biological activity. So that organic matter helps to promote that in the first place, as well as like root proliferation. And sometimes soil amendments are helpful. You'll a lot of times see gypsum as promoted as a decompacting amendment. The reason, the theory behind that is because of the calcium in gypsum. Gypsum is calcium sulfate, so it supplies the calcium, and we'll talk more about that later as far as nutrition. But the thing is that if you don't have enough calcium in the soil, you don't. It's more the calcium to magnesium ratio, and so if you have too much magnesium, it tends to pack the particle. It tends to hold the soil tighter together, and so the idea is by applying gypsum, you're replacing the magnesium with calcium, and you'll get better structure, but not as tightly held together as the magnesium would do otherwise. So it's a matter of that calcium to magnesium ratio. So in cases where you do have too much magnesium and not enough calcium, gypsum can help. But again, it's not one of those instant fixes. Think about it. If your soil's already compacted, how does that calcium get into the soil in the first place? And if you already have enough calcium, then adding more isn't going to help. Okay, so it's just if you do have an abundance of magnesium and not enough calcium where that particular amendment of gypsum is going to help you. So not an instant fix. Here's just some examples of different tillage implements that can be used on turf specifically. Hollow tine cores, that's what we mentioned before, and it's a really large scale version of it. There's rotary decompaction, which slices into the soil. So you can kind of think of it as tillage, but it's really slicing. So it's not turning over the whole soil. It's not disturbing the vegetation to any great extent. You can hardly see that it was there. And this is where the cuts are. Or, I don't know, I see some cuts here too. But anyway, you can see it doesn't disturb the surface too much. It just slices into it. And that just gives you some macroporosity, again, for water infiltration and drainage and a little bit of aeration. It doesn't solve the compaction between those slices, but it starts that process and alleviates some of the problem anyway. And then there's things like the dry ject. Anybody used one of these? Just using air pressure, right? Anybody used a hydroject? Or you all had Dr. James Murphy talking to you last week. He did his graduate work at Michigan State working on the hydroject, and that's just high-pressure water being shot into the ground, similar concept here, to create those channels and fracture the soil a little bit to open up some pore space with very minimal damage to the surface and to the vegetation. Okay, so there are some options there to alleviate compaction even with a turf cover. Okay. So that was the end of my soil structure, the physical aspects of soil lecture. So do we have any questions? I just want to take a pause here before I jump into the chemistry. I know you all love chemistry, so anybody have any questions or comments or experiences you want to share with any of this so far? Jump into nutrition. That's really what I concentrated on when I went through school. But being on the job at the soil testing lab, it's really become kind of my specialty. So we need to know that there are elements that the plant requires. You probably talked about this in your plant biology classes. That there are essential nutrients that the plant requires to complete its life cycle, okay? And this is just a partial list of some of those elements and the relative amounts that are needed in the plant itself, okay, the plant tissue. So you see, like nitrogen can be 2 to 5% of the plant tissue, potassium's 1 to 5%, phosphorus, a fraction of that, 0.2 to 0.5%. Calcium and magnesium are also considered macronutrients. And then about where we get to iron, we start expressing these values in parts per million. Okay, so these are elements that we call micronutrients. Micro doesn't refer to the fact that they're needed less, just that they're needed in lesser amounts, smaller concentrations in the plant. Okay, so they're all essential, but just in different amounts. And and when you say essential, what does that mean? Well, it means that there are certain organic molecules that require nitrogen for them to do what they're supposed to do, or phosphorus. You kind of have to know the biochemistry of the plant to understand where these different elements are needed in the plant. And sometimes it's the enzymes, sometimes they're the building blocks of the structure of the plant. So there's different places where they're needed, and it just depends on what they're doing in the plant as to how much is necessary for that plant. And as I said, we do include that reproductive cycle as part of the life cycle. So some of these elements may not be too important up until the point of that flowering stage, where it's then going to produce the seed and so on. So we'll point out that there are 3 very important elements in the plant: carbon, hydrogen, oxygen. Really, the 3 elements that you think of for any organic molecule: carbon, hydrogen, oxygen. Those come from water and air. Okay, carbon dioxide, oxygen, H2O, water. Okay, so those are taken care of, but every other element that you get that the plant needs is coming from the soil. Okay, and so here, this is just showing you that for each of these elements that I have listed here, where it's important in the plant. Whether it's again structural, or whether it's for enzymes or other biochemical processes where it's needed. And very often, if you know where these molecules are needed in the plant, you have a good idea of what the deficiency symptoms are going to look like. So that can give you a clue. So the idea then is we need to measure in the soil what's available to the plant for it to take up. So on our x-axis here, we have the increasing concentration of a single nutrient. Okay, increasing concentration. Oh, it says in the plant tissue. Okay, well, we're going to relate this to what's in the soil anyway. So, and as we increase the amount of that nutrient in the tissue, you get increasing growth. Okay, well, at least from about here to here, you get increasing growth with increasing amount in the plant tissue and therefore also in the soil. So we have different stages here. We have where it says deficiency symptoms. Okay, that's where the concentration is so low that yes, you're going to see some visual deficiency symptoms because the plant isn't functioning properly because of that lack. Sometimes you'll have hidden hunger, just meaning that you're still deficient, and you know that because you're not up on the top of the graph here, the plateau, but you may not see any deficiencies. But then where we reach that point where it starts leveling off, that's where we decide that's the critical value. That's the minimum value that we need for the plant to perform at its optimum. And that's assuming, we're just looking at one nutrient here, that's assuming that all other nutrients are in their optimum range. Yes?
Sorry, Bobby. Is there a supervisor that wanted the report for this? It's a courtesy to give you guys the case number.
You know what?
It's a gentleman downstairs with the beard, one of the security guys, so that might be best.
Or,
All right,
Should we give that to Fran, maybe?
that's what I was wondering.
Yeah, get it from
Hey, just real quick, sorry.
Yeah,
I just wondered if I could give it to the person that was that's running this class.
Of course.
She'll know more about.
yeah, that's just my business card on the back, has the police report on it, all right?
Perfect.
All right, you have a great day.
Thank you. Thanks for your help. Good work they do. So no, again, we're assuming no other limiting factor other than this one nutrient, and we're increasing that level, and we see the response in the overall plant growth. And sometimes it's, if it's corn, it may be our final yield of seed corn, but in turf, we're looking more at the density of the turf, its resilience to disease, for example, its appearance, and things like that. Maybe its color even. So all kinds of different measures that we can use for that plant growth, but you get the general idea. But at some point, there may be a point where you have too much of a nutrient in the plant, okay? There's too much of a good thing. I always insist, there can be too much of a good thing. Some cases, it's an actual toxicity, okay? Especially those micronutrients like iron, zinc, copper. If you get too much of that, it can kill the plant, okay? In other cases, and this would be more for the macronutrients like calcium and phosphorus, and there it's more usually just an imbalance. You're creating an imbalance, just like, with our nutrition, human nutrition, you need this proper proportion of different nutrients for your body to function properly, and it's the same with plants, right? So, let's see, SS level, yeah. And so we study the life cycles of different types of plants. Okay, so for example, summer annuals are going to have a certain series of processes through their life cycle, certain times of the year. When are they going to need the particular nutrients? Certain times they're going to need a higher concentration or a higher uptake of nitrogen, and at other times of the year or season, whatever their season is, they may need more phosphorus. So we're looking at that also. Winter annuals would be, slightly different just because of the times of the years. Biennials, they have a completely different type of uptake profile, you might call it. And then perennials, where they first establish, and then when they go through the seasons year after year. And even if we look at specifically at grasses, we can compare warm season grasses with cool season grasses. And we know those cool season grasses have their best growth in the spring and the fall here in the northern hemisphere. And the warm season grasses are going to be able to grow and tolerate better those middle of the summer temperatures and sunlight and so forth. So we're looking at those plant cycle, or the life cycles of the different types of plants also to understand when their nutrient needs are. Okay. And just more specifically to the grasses. And then on the top here, we're also looking at this is just cool season grasses, but we're looking at shoot growth versus the root growth and the production of carbohydrates. And here, looking not only, remember that at the same time you're getting that above ground plant growth, don't forget the roots beneath the ground. You can't see them, you can't see the response, but they're affected as well by these cycles. Okay, so we have to be aware of that. So we showed the growth curve for one particular nutrient, and this is trying to show that all of those different nutrients are important, and they have to be in particular proportions. The idea of the most limiting factor, the idea that plant production is constrained by the essential element or some other factor that is the most limiting. So, example here, this barrel is representing all the needs of the plant. Each of the staves represents a different factor and the relative amount of that factor. And so the factor that is the shortest, in other words, in the most limiting amount, is what limits the overall production of the plant. Okay, so in this case, it's phosphorus. Okay, so we can then supply the plant with phosphorus, for example, fertilizer, and it increases the growth of the plant. Okay, and potentially some other factor becomes limiting at that point. But we want to point out then that there are these other limiting factors like water. What if there's a drought? Or what if we have compaction and there's no air diffusion into the soil? What if light is a limiting factor? This occurs, very shady areas of the golf course or in stadiums. Sometimes with real grass, you get a light deficiency, right? And so we have to recognize those as limiting factors too. And if any one of those is a limiting factor, then it doesn't make sense to try to address the problem by applying, for example, more nitrogen. Right? If water is a limiting factor, applying more nitrogen is not going to help. If sunlight is a limiting factor, applying more nitrogen isn't going to help. Okay, right? So that's what I mean by increasing the level of a non-limiting factor will not improve production. Okay, so then we have to understand that these nutrients that we're talking about, how are they taken up by the plant? Okay. Most of the nutrients are taken up. If they're from the soil, they're taken up by the roots, right? There are some cases where you can foliar fertilize, but I'm not going to get into that. We're talking mainly about nutrients that are taken up by the roots, but we need to understand that those nutrients, they're in the soil solution. Okay, the soil water contains ions of these different nutrient elements, and that's how it has to be taken up. It has to be dissolved in the water for the plant to take it up. And this diagram is just trying to show that there are different levels of storage of these nutrients in the soil. Some of them are very relatively available, just like they're comparing it to your money, okay? Some of it's just like your pocket cash, your pocket change, right? So it's immediately available. Plants can take it up very easily because it's already dissolved in the water, okay? If it's absorbed onto surfaces of the minerals, okay, then it can diffuse off of those minerals and into the soil solution and then be taken up by the plants. And so that's kind of analogous to the checking account. You can get it out, but it's one extra step, right? And then on and on, you can think back to where do those ions come from in the first place. They're coming from the weathering of the minerals and from the decomposition of organic matter, okay? So that's more analogous to these longer-term type of investments, for example, okay? So that's the general idea. We're getting those ions generally from the minerals as they weather, from organic matter as it decomposes, and also fertilizers, right? So, and then, so I mentioned, mechanisms of uptake, but realize that this is still going to be the ions dissolved in the soil solution, so it's a matter of mass flow, okay? One example is mass flow. So the plant is taking up water, so it's drawing water into the plant root, and if it's carrying ions with it, that's mass flow. It's pulling in those nutrients along with the water, right? Diffusion is more like you get a gradient of the nutrients in the soil. The closer you get to the plant root, the lower the concentration because the plant's already taken it up, and so the ions are going to tend to diffuse towards the plant root, okay, where there's a lower amount. Just that concept that things tend to try to create an equilibrium, but in this case they never do because the plant root can pick up those ions as they get close enough or they come in contact. So the ions diffuse because of that concentration gradient. And the final way, again, is root interception. So the root's actually growing, extending towards those ions. And it's still being taken up from the soil solution, but it's just that the water doesn't have to move. The roots are growing to that soil solution, to different places in the soil. Okay? And this is just, again, emphasizing that the ions need to be in the soil solution or to be taken up by the plant roots. And just that, all those organisms that live in the soil are really important for helping to make those ions that are in the soil soluble in the soil solution. Okay, whether it's mostly breaking down the organic matter, but also excreting acids, for example, can help to make some of the ions of the minerals more soluble and go into the soil solution where the plant roots can take them up. Okay, so now we're going to look at a few specific cycles. Okay, nitrogen cycle. This is a nice diagram that's trying to illustrate all of the different pathways that nitrogen can take within the soil and then the above ground inputs and losses as well. Okay, so we want to focus on the two forms of nitrogen that are able to be taken up by plants are the nitrate ion and the ammonium ion. Okay, so there's two forms that can be taken up by the plant. One is an anion, negatively charged, and one is positively charged, the ammonium. And so because this is negatively charged, and we remember, I hope we remember, that a lot of our soil particles have a net negative charge. It's very susceptible to leaching because the soil particles don't hold on to anions as easily as they do cations, like ammonium. Ammonium is a cation. So it is electrostatically attracted to the soil particles, okay? Negative and positive. We see there's this process where ammonium is converted to nitrate, for example. And ammonium comes mostly from decomposition of the organic matter. So we see there's a big pool here of organic matter that contains nitrogen, and when it's decomposed, that's what we call mineralization. That's what forms, is the ammonium ion, okay? Other sources of ammonium and nitrate is fertilization, atmospheric fixation. When you have lightning, there's a huge amount of energy that can take nitrogen gas and form ammonium. But otherwise, that process of fixing nitrogen from the air is very energy intensive. That's why lightning can do it. But we do it in, industrial situations. Again, very high energy type of process to fix that nitrogen into fertilizers. And so that's another source of nitrogen, whether it be ammonium or nitrate. And then some of the other loss potentials for loss are this denitrification. Nitrate can be converted to a gas. Okay, this is a bacterial process, usually under anaerobic conditions. Anaerobic bacteria do this. So you can lose it as gas back to the atmosphere under anaerobic conditions. And then there's volatilization. The ammonia can be volatilized as well. Okay, so we see that that's a really complex cycle. So many different pathways. I didn't even mention them all, right? But again, the important things are that these are the two ions that are water soluble that plants take up, and you'll see those names in your fertilizer label, whether it's ammonium or nitrate. The total nitrogen in the soil is mostly in the organic matter. You don't find nitrogen usually in minerals themselves. Okay? There's only really one type of mineral that contains nitrogen. So it's all held in the soil in the organic matter. In the nitrogen cycle, as I just mentioned a couple times, where there's bacteria involved, there's a lot of different processes going on to add nitrogen to the soil or make it available to plants. Now, we're not talking about legumes necessarily in this class, unless you happen to have clover in your turf. Clover is a legume, and do you all know what a legume is? And it's basically any of those plants that have pods, like beans and peas. Some trees, like your eastern redbud and Kentucky coffee tree, and what's some of the other legumes?
Wisteria.
Wisteria?
Does that count? It's kind of like a big green bean pod.
Yeah, it must have been. Yeah, I don't know all of them, but in there's like Lespedeza and vetch, alfalfa, all the clovers, all of those are included. Then you can get into, like the vegetables, like we said, lentils, beans, peas, and then into trees and so forth. But those are legumes. So what's special about legumes? Okay, our biologists are. They fix nitrogen, but the plants themselves don't, right? It's actually the bacteria that live in the roots that they're actually like an infection of the roots, but these are very special bacteria in that they can take nitrogen gas and convert it to a form that the plants can use, and the bacteria themselves can use. But they produce enough of it that the plant benefits, partly because, yeah, they're living right in the roots, okay? They're infecting those roots, and so some of that nitrogen that they fix is immediately available to that plant.
Is that what causes the dark patches of turf around where we have clover and stuff throughout the turf grass?
Extra nitrogen, right? So it's got its own source of nitrogen, and it's not just to the plant. Yes, some of it's going to leak out into
it
the
leaches
soil
into this.
as well. So, exactly. So it's enriching not only that plant, but also the soil around it. There's always going to be those turnover of roots. So that's one really beneficial, symbiosis in that system, in that plant system. And it is very specific between legumes and the bacteria called rhizobia. So, and it's very specific as to which species of legume associates with which species of rhizobia. So you're not going to get that in turf grass, but again, it can supply nitrogen to the surrounding soil as well. But that's just an example, because there are also free-living bacteria in the soil that do the same thing, okay? Just not within the plant roots. They live in the soil and can do the same kind of process. Okay? So it's giving you examples here. Azotobacter is one example for aerobic nitrogen fixers in the soil that live freely in the soil. And then you see there's other processes that bacteria contribute to in that nitrogen cycle. So it's just pointing out, again, the complexity of the nitrogen cycle and the participation in that cycle of the bacteria in the soil. So there's symbiotic and non-symbiotic interactions with the microorganisms that make nutrients available to the plants. And we just want to recognize that, because we don't want to wipe out all the organisms in the soil, because they're actually, many of them, most of them are beneficial to the ecosystem, right? It's an ecosystem. Here's the phosphorus cycle, and you immediately see it's pretty much less complicated than the nitrogen. And we recognize that most of the phosphorus in the soil that's being taken up by the plants is from the minerals, both the primary minerals and the secondary minerals. That's like the clay minerals. Okay, as they weather, it releases phosphorus to the soil solution. Okay, some of it is in the organic form, and as the organic matter decomposes, it supplies phosphorus to the soil solution. And then that can be taken up by the plant, as we said. There's no gaseous forms of phosphorus that we need to worry about, okay? But it shows leaching of phosphorus, but that's usually in most soils, that's a very small component. If you lose phosphorus, it's mainly through runoff and erosion, okay? Because the phosphorus is very tightly held by soil particles, so leaching isn't going to carry much phosphorus. It's not very soluble. But it can easily move, because it's attached to those soil particles. It will move with the soil particles if you have runoff and erosion. So that's a big problem in lakes and streams, is deposition that carries phosphorus with it. And we'll talk more about that later. One symbiosis that's really important in terms of phosphorus is the mycorrhizae. And mycorrhizae is a fungal infection of the roots. And if you look at that word, mycor refers to fungus or fungi, and rhizae refers to root, so it's fungus root. Okay, so, and what's a fungus like? It has hyphae. They grow in streamers, basically, strings of hyphae throughout the soil, for example. And in this case, it's also infecting the root. The fungi grows in between the cells of the root and infects some of the cells there as well. And so it's gaining carbohydrates that the plant is sending down to its roots. But what does the plant benefit from? This is a symbiotic relationship. I just pretty much told you.
Gets water.
It gets water, but also phosphorus. Okay, because phosphorus is so immobile, I said it's insoluble, so it doesn't move very well. So remember what we talked about root extension, why that's important for phosphorus uptake. Well, here the fungus is actually increasing that penetration and proliferation through the soil, able to pick up phosphorus and carry it to the root, and is also very important for water uptake during drought periods. So it's essentially increasing the surface area of the root and how much soil volume is utilized by the plant to take up both nutrients and, as we said, water. Okay. Potassium. Okay, and here potassium is even simpler still. And part of that is because we have no organic matter component to this. If we look back at the phosphorus, again, we have that there is a certain amount of phosphorus in the organic matter that also contributes to the solution phosphorus to be taken up by plants. But with potassium, we don't have an organic matter component. Now, if you remember back to when we were looking at how much potassium is in the plant tissue, you realize that number was pretty high. It was right after nitrogen in terms of how much. So why don't we have any organic matter in this, potassium in the soil? Anybody know? All the potassium is held in the
Solution.
cytoplasm. It's in the cell cytoplasm, exactly. So when the plant starts decomposing, those cells break open, and it's essentially lost. It gets added to the soil, but it's not in an organic form. It's just remaining in that ion form. So you don't see organic matter as part of this cycle. Right? It's coming from when plant residues start decomposing. It adds directly into that solution phosphorus, but you don't have it stored in the soil as organic matter. Okay. But otherwise, secondary minerals, the clays, and the primary minerals, like the feldspars, as they weather, they release that potassium as well. But you see, it's a much simpler cycle, much less complicated cycle. But it, if you understand these different cycles, you can have a good idea, a better idea of how to manage them. Okay, so if you have a deficiency, what happens? And we mentioned this earlier. You get, in extreme cases, you'll see some deficiency symptoms, again, related to the function of that element in the plant. Okay, so I won't go through all of those, but there's some examples for you. And some references. These will show you some of those visual symptoms if you want to get an idea of how to interpret those. So as we mentioned, different types of plants, and sometimes very specific to the plant species, are going to have different needs in terms of their nutrients. Okay, so it can depend on the nutrient itself and for each plant. Sometimes the climate or the weather conditions will contribute to different needs as well. But this is just showing you that the phosphorus, soil phosphorus in the soil. So this is showing you one of those response curves, increasing amounts of available phosphorus. So you read this as extractable phosphorus is what's available to the plant. And you just see that, different types of plants have different needs, and increasing amounts of the needs of the nutrient increases the growth, and each of these different crops has a different critical value. Okay. So this is what we use in terms of making recommendations. We don't necessarily change our interpretation of the values, but we will adjust the recommendations based on what the plant type is. Fertilizers. So most fertilizers or mixed fertilizers have the three components: nitrogen, phosphorus, and potassium. And I have to point out that the fertilizer grade, or those three numbers that you see on a fertilizer label, are percent nitrogen, percent PTO5, and percent K2O. Okay? So we often say NPK, but realize that the phosphorus and the potassium percentages are expressed in oxide form, and so that means the actual phosphorus content is lower, because you're taking the oxygen content into account also when you're figuring the percentage. Okay, it's by weight. So those are the three numbers you'll see that on most mixed fertilizers. A lot of times now the middle number will be 0 for established turf, because in a lot of soils we've accumulated excess. Water insoluble nitrogen is also an important factor that refers to the amount of nitrogen that is slow release. It's not immediately soluble, and so that means it takes some time for it. So it's water insoluble, so it's slow release. Sometimes other nutrients are indicated, like in this case, they're also mentioning how much calcium is in the product, how much magnesium is in the product, sulfur, some of the micronutrients as well. Okay? And very often, you'll get the source of those nutrients. Okay, these are the nutrients. How did they come up with this formulation? And this is what they used to create this product. Okay, so sometimes that's important. Always choose your fertilizers based on what your soil test tells you. I completely lost track of time here because of our little 2:30. So I have another hour. We're good. Okay. So always do your soil test before you select a fertilizer. We at the Rutgers Soil Testing Lab, we use the ratio of the required nutrients. So, for example, a 1-to-1-to-1 ratio. Absolutely.
Guys, I apologize if you guys had a scare there. I don't know what happened. I'm highly allergic to nuts, so anytime I come in contact with them, I go into anaphylactic shock.
Oh my gosh.
I don't even remember being in the classroom or anything, so I'm not really sure what happened, but we just spoke, and I guess he took me up from here. Thank you, whoever heard the reason and everything.
Nice to have you back.
Yeah, they gave me a
Yeah.
All right.
Yeah.
Yeah, so I apologize for scaring you
No.
guys. It scares me just as
We're
much.
glad you're okay. We were.
Yeah, thank you. I don't know.
Yeah.
Sorry about that. You know.
It was right after you left, Steve, like, oh my gosh.
Yeah, he said he was going to get a haircut.
My haircut. All right, okay, we're very happy, this is John, we're very happy you're back. If anything bothers you, just let us know immediately,
Yeah.
okay?
Fall asleep, I'm gonna
Yeah, exactly.
Oh, wow. I really glad you're back. And if you have any questions over what you missed, just let me know. All right. Thanks, Steve. Yeah. So So we give you the ratio of nutrients, and so this is intended to be the ratio of percent nitrogen to percent PTO5 to percent K2O. So a 1-to-1 ratio can be met with a number of different fertilizer grades. Okay, it could be 10, 10, 10, 17, 17, 17. I know it's 1, 20, 20, 20. You know, it doesn't really matter what the actual concentration is. You want to get that correct ratio of the nutrients. And if you can do that, then applying it at the rate for nitrogen will also give you the correct amount of phosphorus and the correct amount of potassium. Okay, so that's why we do it that way. In some cases, of course, the manufacturers, the fertilizer companies, do not always have these grades available that we recommend. And then sometimes you'll have to supplement. If we say, for example, maybe a 1-2-3 ratio, just making that up, but there's probably not a fertilizer out there that has a 1-to-2-to-3 ratio. So you may have to get a 1-1-1 ratio fertilizer, and then also add some phosphorus, and get a phosphorus only fertilizer, and also get a potassium only fertilizer to supplement that. Or you might be able to get a 1-to-1 ratio, and then just be able to add just the phosphorus to get up to that 3. Okay, so that's why we express it that way, because for one thing, keeping up with all the fertilizer grades that are available out there is a job in itself. So we tell you what it's needed. We try to help you with that ratio of nutrients, but then it's a matter of sometimes of if you can't find it, then doing some figuring as far as trying to meet each of those needs individually. Okay, this is, you probably won't deal with this too much. It's more for like the homeowners, for example. There's a lot of fertilizers out there that are labeled for roses or for vegetables or for trees, and again, it's more they're assuming you haven't done don't know what you need, so don't rely on that, because they don't know what your soil is like. That's why you do a soil test, so you know what you need. Be careful, always read the labels. We've always got to say that. Know what's in it, and understand what you're applying and what the proper rate is. We do like to encourage use of organic fertilizers. Generally, they tend to have a low analysis, which will mean that you need more to get the proper amount, but you always then have a lower risk of, you don't want to get too much and burn the grass, for example. So you have a lower risk if you start with a low analysis. And then you're oftentimes adding organic matter at the same time, which has its own benefits, as we've mentioned before. Okay. I wanted to mention, going back to that example again of the 1-to-1-to-1 ratio fertilizers. So you understand that, as I said, you can use 10-10-10 or you can use 20-20-20, but it's just a matter of how much you apply then. If it's 20-20-20, it's twice as concentrated as 10-10-10, so you only need half as much, right? And the label should tell you that, how much is proper to apply. But just pointing, that's why you can use any one of those. Sometimes I get questions about, oh, that's so much more concentrated. I'm like, well, then you just apply half as much, So hopefully that's clear. In some states, including New Jersey, the application of fertilizers to turf is regulated. There are some general recommendations for everybody, including homeowners, like the blackout dates and the total amount of nitrogen you can apply and so forth. But There are some that also apply specifically to professionals. You have to be certified. You go through a training and take a test to become certified, or you can take the same course, but just do it at a trainee, a level where you're, what do they call it, a trained fertilizer applicator, where you're supervised by someone who's certified. Okay, so in New Jersey, that training program is called ProFact. It was developed here by James Murphy, and you can go and look at that online, and you can read all the materials without any costs or anything. It's just when you want to take the test and become certified that there is a cost to it. Sometimes there are these calculations needed, as I mentioned. You know, if you find the correct fertilizer grade, again, it'll usually have the right rate of application that's needed. But if you don't find the exact ratio that you need, you might have to do some of these calculations to figure out, okay, how much of the supplemental nitrogen or supplemental fertilizer do I need? So I obviously can't go through those calculations with you right now, but sometimes I'm just pointing out that that's going to be necessary if you can't find that perfect ratio of nutrients. And as always, you need to calibrate the equipment. Okay, so even if your label tells you at what or what amount to apply per 1,000 square feet, for example, you have to make sure that the equipment that you have is applying it at that rate. Okay, sometimes there'll be some general guidance on that with your manual. But it's always a good idea to go through that calibration step and make sure. It's going to be somewhat dependent on how fast you walk, for example, right? If you're doing it manually like that. So calibration of equipment can be really important to get that proper amount as well. So here we see that kind of graph again in terms of amount. In this case, we are specifically saying soil test level, and we see the growth curve in response. We see that critical level, minimum amount to get the optimum plant growth. And so those different categories that we have are how we classify the values, okay, the different values that are along this soil test level axis are classified as either very low, low, medium, high is the same as optimum, and then very high is excessive, more than you need. Okay, and so I'm going to make the point that number one, that critical level, I said it's that point where you get the maximum growth, but also realize that with every increment that you're increasing that, say with fertilizer, you also have a cost as well, right? So sometimes that economic increase isn't worth the extra fertilizer. Did I say that right? Are you going to get that much increase in growth or quality, turf quality, with that extra 10 pounds of fertilizer? Okay, so there's that economic aspect to it as well. You may not want to get exactly to the critical level. And you certainly don't want to get to this point where you're going into the excessive. It's not doing any benefit for the plant and can actually harm the plant. So keep that in mind. There is such a thing as too much of a good thing. And to further illustrate that, this chart, this is showing for different nutrient elements, both synergisms, which are shown in green, and antagonism. So when I was talking about balance, having the proper balance, This is why you don't want to get too much of one particular element. So for example, here's nitrogen, and you see it shows an antagonism with copper and with potash, potassium, and with boron, just for example, nitrogen. And you see all those other red lines. So it's meaning that if you get too much of that particular element, it's going to interfere in some way with the nutrition of a different element, whether it's uptake in the first place at the root surface, or whether it's the function in the plant that it's supposed to do. Okay? That antagonism may prevent that element from either being there in the first place or from working properly as it's intended in the plant. Okay? So again, there is such a thing as too much of a good thing. So when we have a below optimum nutrient level in the soil, we're going to be applying a higher amount of nutrient. Okay, just makes sense, right? And as we get to the optimum, we may be still adding some, but just to maintain it at that level, because we recognize that, yeah, the plant's going to be taking up some. Maybe we're going to lose some through some of those leaching processes or denitrification, for example. So we do make some maintenance applications even when it's in the optimum range. But when we get to that above optimum, we want to stop our applications, go down to zero with that nutrient application so that we can draw down that level in the soil. Okay, because we don't want to reach that over-fertilization range. Over time, we want to, we're going to be bouncing up and down as we add fertilizer, but we don't want to get into that range where we're over-fertilizing, just like we don't want to, we don't want to get into the deficient stage as well. And so that's why we do soil tests on a regular basis to try to maintain it in that zone. And I'm pointing out also that in addition to the possible problems of excess nutrients in the plant itself or in the plant soil system, there's the environmental risks as well. Okay, whether it's nitrate poisoning of groundwater. Nitrate is toxic at certain concentrations, so we don't want to get high nitrate levels in our groundwater. Anybody heard of blue baby syndrome? Okay, that's what happens. Basically, it prevents the oxygen from being taken up by the blood, red blood cells. So that's one of those possible public health dangers of having too much nitrate leaching to the groundwater. But more evident usually, and especially lately, is the nutrient pollution that happens in our waterways. When you see that green surface of your ponds or lakes or even in the streams, that's from nutrient pollution that's producing too much algae. And what that does ultimately is when that algae starts dying off, it consumes all the oxygen in the water, and that kills off the aquatic life, fish and so forth. So we want to prevent that as well. And I'll just point out, that that's why we have regulations. That's why there is a fertilizer law in New Jersey, is because there was there still is nutrient pollution. It wasn't, an instant fix. But when we have these things happening, that's when these regulations start, showing up in response to that problem. So we got to be aware of that and try to prevent that from happening. So in terms of nutrient stewardship, then this is one of the programs of the International Plant Nutrient Institute, the 4 R's as a guidance for fertilization. And it's usually used in crop fields, agricultural fields, but the concepts are there for all of us. Use the right source. In other words, know what your soil needs, know what your plants need and relative to what the soil has. Apply the fertilizer at the right rate. Do it at the right time of the year when those nutrients can be utilized effectively by the plants. And place it properly, again, so that they can be utilized and not lost to the environment. Okay. So here, I've mentioned that the eutrophication process from nutrient excess in fresh water, like streams and lakes and rivers, that's usually due to phosphorus. Phosphorus is the limiting factor in the freshwater systems. So if you get erosion of soil particles with phosphorus attached and it gets released to that water, that's what causes eutrophication in those systems. Whereas in salt water, especially like here, the Barnegat Bay or Chesapeake Bay, or in the ocean, like the Gulf of Mexico. Anybody heard of the hypoxia zone in the Gulf of Mexico? Okay, that's what's happening. It's from nitrogen in that case. Nitrogen is the limiting factor. So when we're adding it through leaching, for example, from our soil, it's creating all that biological activity which uses up the oxygen in the water and can kill the aquatic life. Okay, so let me just close this down and we're not done. We'll talk about pH. Okay, usually in a standard soil test, you'll get the nutrient analysis, like those nutrients that we were just talking about. But the other very important part of the soil test, a standard soil test, is the soil pH. So, everybody remember from high school chemistry what pH refers to?
Power of hydrogen.
Oh, good. Power of hydrogen. So it's actually a measure of the concentration of the hydrogen ion in the solution. Okay, so this represents concentration of hydrogen, the hydrogen ion. That's what's acidic, right? And so we see the scale generally goes from 0 to 14. They don't go all the way up to 14 here, but technically 7 is the middle and 7 is neutrality. So at that point, the hydrogen ions are at the same concentration of the hydroxyl ions. You take water apart and you get the hydrogen and you get the OH, the hydroxyl, right? So at 7, they're equal amounts of hydrogen and hydroxyl. So it's all neutral. That's what makes it neutral. Okay? And as you go down, meaning as you go down in the scale, I'll tell you what it means in a minute, you're getting more acidic. So on the left-hand side here, you see we're relating that to some of the things that you can relate to, like beer and coffee, right? And vinegar and lemon juice, and finally battery acid down here. So increasing amounts of acidity. Above that, you're getting less hydrogen ions, and you think about seawater, baking soda, antacid, the opposite of acid, neutralizes acid. So the higher you go, the more alkaline. And you see then what the actual concentration of the hydrogen ion is for 3 examples here. So at neutrality, the concentration of hydrogen ions is 10 to the negative 7. So it's really still a really low concentration, right? But it's the negative logarithm, that 7 represents the negative logarithm of the concentration. So that means that as the pH decreases, okay, you get a higher concentration, but it's not just like 2 units, it's 100 units more concentrated hydrogen. Okay, Okay, so this is a log scale, so it's on the basis of 10. So, and likewise, as you go from pH 7 to pH 9, this pH 7 is 100 times more concentrated in the hydrogen ion than at pH 9. Okay, so I'm just trying to show you that when just going 1 unit doesn't sound like much, but it's really 10 times fold difference. Okay, and so on the right-hand side here, we see where you find where different types of soil might fall into this range. Most of our soils in this region, in the forested, where it was native forest, are going to be between 4 and 6. Because of hundreds of years of liming for agricultural use, we're also can go up in the between 6 and 7, for example. You do have some of these acid sulfate soils in New Jersey, and hopefully you'll never encounter those because they can go down to pH 2. And then as we go further west and we get into calcareous soils or limestone soils, for example, you can get these alkaline pHs. And when you get to really dry, arid regions, you might have these sodic soils where the pHs are above 80. So there's quite a range, across the globe of the different pHs that you might encounter. But again, depending somewhat on, those soil-forming factors that we mentioned way back at the beginning. But why is soil pH so important? And especially, how do we associate that with, nutrient content? Well, one of the reasons soil pH is so important is because it affects the availability of these different nutrients. Okay, so you might have plenty of, for example, phosphorus in your soil, but if your pH is too high or too low or too acidic, it's just insoluble. And remember I said it has to be in the soil solution for the plants to be able to take it up. So we need to have that pH range where the nutrients are soluble in the soil solution. Okay. So, sorry, I should point it out at the beginning, the pH scale is at the top there, 4 up to 9, includes most soils anyway. And the relative width of these bars represents its relative availability for plant uptake. Okay, it's relative solubility. So we see at high pHs, there are some elements like molybdenum, calcium, and magnesium. They're going to be very available. Okay. But there's others like copper, iron, and manganese that are very insoluble and poorly available. And on the other side of the scale, very acidic situations, you can get deficiencies of molybdenum, phosphorus, calcium, and magnesium, for example. And so, if you had to choose your soil pH, where would you choose it to get the balance of availability for each of those elements?
6.5.
Yeah, right. Between 6 and 7 seems like especially with phosphorus. Okay, so 6 to 7 is often considered the ideal range. The other thing that I point out here is aluminum. Now, aluminum is not a nutrient, and in fact, soluble aluminum is toxic to plant roots. Okay, so we see here that as we decrease pH below about 5.5 or 6, somewhere in between there, the more acidic it becomes, the more available, the more soluble aluminum is. And so then you start getting limitations in root growth because of soluble aluminum. Okay, so that's the other important thing about soil pH related to plant nutrition and root health, so to speak. So, as we said, most plants grow ideally or have this optimum pH range between 6 and 7, somewhat related to availability of nutrients. But we do recognize that there are other plants that are tolerant of other soil pH ranges. Some have relatively wide tolerance for soil pH and others relatively narrow. When we get down to these plants that actually do perform better under acidic conditions, we call those acid-loving plants. And here's just a few examples, like a lot of ornamental plants, azaleas, hollies, rhododendrons are some examples. Pine trees, spruce, some of the conifers. And then in terms of crops, blueberry and cranberry go even lower. And think about that. These were native to southern New Jersey. And think about the soils that were there. So these plants co-evolved with the development of those soils, which are very sandy and very acidic. Okay, so they have the mechanisms to avoid the problems that the other plants would have at those soil pHs. So it's a matter of evolution and adaptation to those conditions that make that possible. On the other end of the scale, there are some plants that prefer it even slightly alkaline, partly because of their demand for calcium. The legumes, for example, tend to like it 6.8 to 7.2, for example. Anyway, so in our climate here in New Jersey and in the general region, there are processes going on in the soil that are naturally acidifying the soil. Okay, so some of that is, just the respiration that occurs in the soil, as I said, produces carbon dioxide. And when that carbon dioxide dissolves in water, you have carbonic acid. Okay, it's an acid. It's a weak acid, but it does add to the acidity. Some roots and some of the bacteria, for example, exude organic acids into the soil. That tends to increase the acidity. The roots, when they take up cations, they need to maintain this electrostatic balance, so they're exuding hydrogen ions into the soil. Okay? This diagram is actually showing the color response is due to acidity that's produced as the roots are taking up ammonium ions, ammonium nitrogen, which is a cation, so it needs to exude hydrogen as it does. And so it produces that intense acidity right in the zone of the roots. Okay? And if you did that with nitrate nitrogen, you would see just the opposite. It tends to become more alkaline around those roots because it's exuding hydroxyls to balance the nitrate. But part of about our region here, the acidity in our soils here is partly because of the leaching that occurs. We get enough rainfall that we're leaching some of those cations, calcium, potassium, and magnesium. They're considered basic cations. Okay, whereas hydrogen is an acidic cation, right? Well, calcium and potassium and magnesium, as you displace those, the hydrogen ions are taking their place. So that becomes acidifying. And then there's other processes, oxidation of ammonium, like ammonium fertilizers, sulfur, iron. So those are natural biological processes going on in the soil, but again, producing acid as a byproduct. So just so you understand that it is a natural process in our region here, at least, for soils to become more acidic through time. We counteract that in our management strategy by applying limestone to soil. But how much do limestone should we use? Sometimes we acidify the soil. Maybe some azaleas and rhododendrons, and our soil pH is too high. So how are we going to do that? So first we'll talk about reducing acidity. And again, limestone is what we're using. And this is showing the process that's occurring. That calcium carbonate there is the limestone, okay, the major component of limestone. And you see that it reacts with the hydrogens that are absorbed to the clay surfaces. And in that process, it's producing ultimately water and carbon dioxide. So it's neutralizing that acidity by turning it into water, basically. Okay? So I point that out because I want you to know that it's the carbonate part of limestone that's neutralizing the acidity. Okay? It's not the calcium, it's the carbonate that neutralizes the acidity. There are some other limestone products. Burnt lime is one, hydrated lime. You'll see these names, sometimes called slaked lime. They're not nice to work with. They tend to cake and they're caustic, so they're not as nice to work with. They do work more rapidly and they are more concentrated, but they're usually avoided just because they're really difficult to work with, especially that caking factor, so they don't spread nicely, for example. So our limestone recommendations, it depends on how much to apply, depends on these things. The difference between our target pH and our existing pH, how much acidity do we need to neutralize, in other words. Also, what is the buffering capacity of the soil? What's a buffer?
Resist change to pH.
Okay, a buffer resists change. Okay, so the soil itself is able to resist that change, and I'll show you why in a minute. And then characteristics of the limestone product itself are going to determine to some extent what you use and how much. So the buffering capacity of the soil, what we can do is estimate it based on soil texture. Again, importance of soil texture, because coarser textured soils are poorly buffered, whereas finer textured soils are more highly buffered. They're able to resist the change. But more commonly now, we are actually going to measure the buffering capacity of the soil so that we get a better recommendation for you. This is just showing differences in types of limestone product. You've probably heard the terms calcitic limestone or dolomitic limestone, and this is just showing you that there is a range. Okay, pure calcitic limestone is about 40% calcium. Okay, whereas if you go pure dolomite, which is the maximum amount of magnesium that you can have, you'll still have about 22% calcium in it. Okay, when I say dolomite, that doesn't mean it's just magnesium carbonate. It still has some calcium carbonate, but it's also going to have about 13% magnesium in it. Okay, so realize that dolomite still has calcium in it. It's just that it also has magnesium in it. But again, it's still that carbonate part of it that's doing the neutralization. When we make a recommendation for one or the other of these, it depends on the relative amounts of the nutrients in the soil. If you need some magnesium to get out of that deficient range, we'll recommend the dolomitic type limestone. And so, and I'll just say, remember when I say pure dolomite, that's the extreme. There's a range between that 40% calcium and that 22% calcium, and 0% magnesium up to 13% magnesium. So there's a range. It's not either just one or the other. There's going to be a range. But then calcitic limestone we would apply whenever your magnesium level is optimum or above. And if you don't need magnesium, we're not going to ask you to put any down. That's partly related to what I said before about there being, there can be too much magnesium in the soil and the effect that it has on the example, this label, it's giving you a whole lot of different information. It's giving you elemental calcium as well as the calcium oxide, calcium carbonate, and the calcium oxide you perform that you can express this information. But this one happens to be 21.4% calcium and 12.1% magnesium, so it's pretty close to that dolomite. But we have to determine, because magnesium carbonate is actually more, because it has a lower atomic weight, magnesium does, than calcium. It has a more concentrated effect on neutralizing the acidity. So it's more effective, in other words, in neutralizing the acidity. So we have to put them on a basis where we can understand the relative effectiveness of these products. And so we use this calcium carbonate equivalent. So if you had 100% calcium carbonate equivalent, calcium carbonate, it would have 100% CCE. Okay? How does magnesium carbonate, or the dolomite, compare to that? Well, dolomitic limestone usually has a higher calcium carbonate equivalent. In other words, as I said, it's more effective. And again, just because it's more concentrated. And so here, calcium carbonate equivalent right there is 105.6%. Okay, so it's more effective than pure calcium carbonate. That's because of the magnesium carbonate in it. Okay. So, so you can use that to determine how much is actually needed to do the neutralization that you need. But the downside of using a dolomitic, in addition to if you don't need the magnesium, don't use it, but it is less soluble, and so it's going to react more slowly. And then there's another value on that label called the effective neutralizing value, and that's trying to include the factors related to size. So down here on the bottom, you see they've done some sieving of the particle sizes, and they're going to rate this product based on those numbers, because what's the size going to have to do with it?
How quickly it dissolves in this slide.
Right. Remember, the smaller you get, the more surface area, the more soluble it's going to be. The more reaction you'll get because of the size. And that's what I'm saying here. So the products themselves can be called pulverized, and that's just, completely powdered, broken down to the smallest pieces.
Granular.
Yep, granular is going to be the
Brittle.
largest. Pelletized is kind of in the middle, where they've pulverized it and then reformed it into pellets, and that tends to be relatively good. I just included down here some of the factors that they use, when they're looking at this. In New Jersey, they don't use the same sieves that they mentioned here, but there are laws that govern use or characterizing the products. Okay. And so, how does limestone react over time? When you apply it, it's not an immediate reaction. As I said, for example, magnesium carbonate takes longer to react, and even calcium carbonate isn't really soluble, and therefore the importance of the size as well. But you see here, it can take almost a full year for a limestone product to react in the soil. Depends on many different factors, but in other words, it's not an immediate fix to a soil pH problem. And the other thing that this shows then also is that, again, in this case, there's all these acidifying processes, natural processes that are occurring in the soil that bring the pH down again. And so it is something that does have to be done periodically. How frequently it needs to be done depends on the buffering capacity of the soil. So, after you do soil tests, frequently every 2 to 3 years for a while, you will get a sense of how frequently that needs to be done. You'll get an idea of the buffering capacity of the soil. So over time, you'll understand that. As mentioned, the soil texture has a big effect on the buffering capacity of the soil. Sands are poorly buffered. Clay loams are very highly buffered. And so you see how that affects the amount of limestone needed to raise the pH for each of these cases. We're using a target pH of 6.5 in all of these cases. And each line represents, this is a half unit increase, this is a 1 unit increase, but notice how that required limestone increases with increasing fineness or increasing buffering capacity of the soil. And so this is explaining the buffering capacity. How does soil resist this soil pH change? Well, clays and organic matter, and remember they have this charge on them. I mentioned this for clays, but organic matter also has charges. And so it's absorbing some of these ions, including hydrogen ions, the acidity, onto those surfaces. And it's in some type of equilibrium with what's in the soil solution. So if we were just to apply enough calcium carbonate to neutralize what's in the soil solution, there would be an immediate response of the hydrogen ions that are on the clay particles and on the organic matter to try to restore the hydrogen ion or try to equilibrate the hydrogen ion concentration that's in the soil solution with what's on the surfaces. Okay? Again, it's trying to even everything out. But this, meanwhile, is what we're measuring in the lab. We're measuring what's in the soil solution. Okay? You can't take off what's there and measure it here. So, well, actually you can. That's what we do when we do a buffer pH. But so what's held on those surfaces is what we call the reserve acidity. Okay, and again, as soon as you neutralize what's here, it's going to try to restore the hydrogen ions in that solution. So again, we do actually measure what's on these surfaces by what we call the buffer pH. If you've done a soil test before, maybe you've seen that term, buffer pH, and this is what it's referring to, is that we're adding a buffer that's resisting, that's basically competing with the soil particles for those hydrogen ions, and how much, then we measure the pH of that mixture of soil and the buffer, and how much it changes the soil pH, or how much it changes the buffer pH, whatever that equilibrium point is, tells us what the buffering capacity of the soil is. And so from that, then, we can give you an accurate estimation of the amount of limestone needed to neutralize not only what's in the soil solution, but what's also held on the reserve. Okay? I mentioned this, again, the carbonate is what's neutralizing the acidity. It also does, is a valuable source of calcium. Okay? And so you'll often see this really close correlation with the calcium content and the soil pH, but I have to point out it's not always the case. Sometimes we've had some soils where the pH was really low, but the calcium was really high. And the question is, well, where did that calcium come from? Why isn't the pH higher? Oh, you must be wrong. Right? But a lot of fertilizers also include calcium. Okay? that aren't carbonates. Okay, calcium phosphate, your common source of phosphorus in your fertilizers has calcium in it, and so on. So there are other sources of calcium besides limestone, but it is a very good source of calcium if you also need to change your pH. If you don't need to change your pH, but you have a low calcium content, which can also happen, then we usually recommend gypsum, agricultural gypsum. So that will increase your calcium content as well as your sulfur content, but not change the soil pH. Okay. What if your soil pH is too high and you need to lower it? Sometimes that's from over-liming. Just, we have those old grandpas that get out there every spring and every fall with their limestone, and it's just one thing they have to do to take care of their lawn. But it does build up and make the soil too alkaline sometimes. But sometimes it's due to, you have that limestone type bedrock, and that can also lead to high pHs, especially if you're going to grow one of those acid-loving plants. And as I mentioned, in arid environments, you don't have that same leaching environment that we have here in New Jersey, and so those calcium can and other salts can tend to accumulate in the soil and result in higher pHs. So sulfur is the usual thing that we recommend for acidifying the soil, and not the sulfate, but elemental sulfur, a reduced form or neutral form of sulfur, because it's the actual oxidation process and another biological process, oxidizing sulfur to sulfate produces hydrogen ions. You're basically producing sulfuric acid, and in that process, acidifying the soil. And there are two other products that are sometimes used, and you'll notice that they have sulfate in them, but it's not the sulfate that's doing the acidifying. And in these cases, in case of iron, it's another oxidation process where you're changing the +2 form of iron to the +3, and that's an oxidation. It produces hydrogen. In this case, it's the aluminum that's going through hydrolysis. It's breaking water into OH and H, and the OHs react with the aluminum and leave the hydrogen ions out there in the soil solution. So they're different processes, but all of these are different are acidifying processes. And you could also sometimes use certain organic products like pine needles, or especially sphagnum, peat moss is often used, especially when you want to add some organic matter as well. And this just showing again different soil textures. You're in this case we still have that target of 6.5. I probably should have chosen something more like 5.5 for our acid-loving plants, but the point is, with increasing buffering capacity, you need more of that product to get to the pH, the target pH, for each of those lines. Okay. Again, these different elements exist in a soil solution as ions, and so there's the cations, positive charged ions, and the anions. Okay. So we'll talk about this cation exchange capacity for a minute. So this is supposed to represent a soil particle, especially a clay particle. Remember how I said they're relatively flat, like plates or like cards? So that's what this is supposed to represent. And it has these negative charges on it, okay? And that's just built into the crystal of that clay crystal. But it's absorbing these ions, these cations, because of that electrostatic attraction. And so that's what we call cation exchange capacity. Okay? And the idea of exchange is that they do come off. They're like magnets, they're attracted to it, but they'll come off in response to diffusion towards the root, for example. But it's always going to be replaced by another ion, cation, to take the place on that crystal. So the more net negative charge it has, the greater cation exchange it has. These also can have anion exchange capacity, because there can be some positive charge on the crystals, and especially on organic matter. But the idea then is that this is also serving as a reserve of nutrients in the soil. What's being held on that cation exchange capacity is a storage, it's a bank for those nutrients. So before we were saying that was like the checking account. Remember we mentioned it's not what's in your pocket, that's what's in the soil solution. It's what's in your checking account. It's absorbed to these soil surfaces. And so there's diffusion. Here's your soil colloid. Colloid just means really tiny particle like a clay or organic matter. And it has a net negative charge. It's absorbing cations. It has some places where it can also absorb anions, but it's in equilibrium with what's in the soil solution. And then that's able to be to diffuse to the plant roots to create that equilibrium. Okay, so we want to have a management plan. We do a soil test. We're going to evaluate the recommendations and implement them, and then keep track of everything over long term to develop a plan for long term. This is what a soil test kit looks like at Rutgers anyway. Basically just, it's an envelope to put your paperwork in, this questionnaire you fill out. It has some sampling instructions for you to be able to take a good sample. And then this envelope is attached to a canvas bag. You put the soil sample into so you can mail it to us. That's what it looks like. What I really have to emphasize to you, though, is that the sampling process, which you are responsible for, is a really important part of the whole process. Okay? It's that concept of garbage in, garbage out. You don't want what you put into the soil testing process to be garbage, because the results that you get, the recommendations, won't really be valid or useful. Okay? So if you're going to go to the effort of doing a soil test, which I insist you should, but make sure you take a good representative sample so that the recommendations that you get are really valid and best, management practices. Okay, so the idea is that you're going to define a particular area. It should have the same soil type within that area, and it should all have been treated the same for a long time. Another example is you don't want to take a sample from your garden and a sample from your lawn and mix them together and assume that the results are going to be good for both your garden and your lawn. Okay? It doesn't work that way. You know that they're going to be different, so sample them separately. That's the general idea. So define your area and then take multiple subsamples from that area. So, you don't want just one core to represent, 5,000 square feet. Take multiple subsamples, blend them together, homogenize it, and then that'll be a good representative sample. You can if you have a soil probe, that's the best. If you guys are professionals, you should have one of these on hand to get your samples. It makes it really fast, really easy empty your subsamples into a clean bucket, and when you get enough of them, like 15 to 20 samples for that area, homogenize it in that bucket and send us a sample from that. This is just saying, control the depth of sampling as well. Ideally, you'll dry the sample. We'll do it if you don't, but it is a step that we have to take, so it kind of slows down the process if we have to do that to any extent. Fill out the paperwork as best you can. Sometimes we get samples in that people haven't even told us what they're growing, so how can we give them recommendations? So usually we get responses back to you in 1 to 2 weeks, depending on how busy we are and other factors like, is the sample really wet? Well, it might take a while to dry. So for a basic soil test, again, you get the nutrient levels and the soil pH. There's some other tests that we do that you can also request. This is from a soil test report. This is our results for soil pH, where the green area is representing the target range of soil pH. And the little arrow there shows the result. And so you see it, in this particular case, it's right at the lower end of the optimum range. Okay. For nutrient levels, all of the nutrient levels in this case were off the charts, okay, excessive. But in addition to the representation, we say either adequate, low, or high. There's 3 categories: low, adequate, high. And then we'll provide recommendations as well. One other thing, it's 3:30, I can tell. I just want to point out another part that you'll get especially for golf course reports.
Take another 10 minutes.
I will keep going as long as somebody's here. So. For golf courses in particular, we'll also show this calculation, which is based on the nutrient levels here. We've taken the calcium, magnesium, and potassium, the 3 cations that you see up here, and estimated, and also the hydrogen from the acidity, and estimated the cation exchange capacity. Okay, so we can take the data that we already have from up here and estimate the cation exchange capacity. And then we tell you the relative proportion of calcium, magnesium, and potassium that are adsorbed onto those cation exchange sites. Okay? And then at the bottom of this table, we see this is what's suggested as a good range that would correspond to this optimum range. Okay? So we want about 65 to 76% of calcium on the, or 65 to 76% of the cation exchange capacity should be calcium, and 10 to 15% of the cation exchange capacity should have magnesium, and so forth. Okay, so those percentages, the actual percentages are here, and then you can compare them to what would be ideal. And so that's again useful when you're trying to figure, do I need a dolomitic limestone if I'm trying to lime? Well, in this case, you have more magnesium than calcium in the optimum range. We would tell you to use a calcitic limestone. Okay. Okay. How far do I have to go?
We're past 3:30.
I know I'm at time. Well, I hope you can read through the rest of the slides that you have in your paperwork there. But there are ranges that are suggested, and this whole concept was actually developed at Rutgers, but it's not, widely accepted as a scientific tool to manage. We do give it to you there for reference purposes. It does have some value, but just don't try to use it by itself to manage your soil levels. So this is just about implementing those results, interpreting the different values on a soil test report. This is giving you, specifically from one of our Rutgers Cooperative Extension fact sheets, how we make the nitrogen recommendations. And again, this is going to be all, except I think there's one case for, zoysia grass. But the rest of this is cool season grasses. So you'll see the difference between warm season and cool season grasses. You'll see the differences in management level or, different factors here like irrigation and whether you recycle your nutrients by returning your clippings to the soil. Okay, again, we want to try to stay in that central range, never applying too much and never getting deficient. Right? Oh, I think I reached the end. These are just a bunch of different fact sheets that are available through the publications list on the website. So go through that and see if there's some more information there that you can get yourself online. Okay, thank you. Thank you. It's my pleasure to be here.
Thank you very much.